Hello and welcome to a special edition of the Knowledge Distillation podcast. In this episode, we are eschewing our usual interview format to take you through the Graphcore research team's Papers of the Month. As part of my job at Graphcore, I get to work alongside the company's hugely talented AI research team. When they're not developing their own techniques to help advance artificial intelligence, they are monitoring the wider AI landscape to understand the key research that is pushing the state-of-the-art forward. Today, I am joined by Charlie Blake, a research engineer at Graphcore. As Charlie explains, Papers of the Month is a super valuable internal resource at Graphcore that we're now making public as a blog. And in this episode, Charlie talks us through January's Papers of the Month. Hi, Charlie.
Hi.
Good to see you.
Thanks for having me on.
So can you start by introducing us to your team, the Graphcore research team? Explain to us, why does Graphcore have this in-house research group and what are the main focus areas that you are looking at?
Yeah, so the Graphcore research team is really, as you said, our sort of in-house AI team within Graphcore. Graphcore as a whole makes chips for AI, and it's the research team's job to be, if you like, the experts within the company about the algorithms and models. So it's our job, firstly, to really provide, knowledge to the rest of the company about the current state of AI. So we need to stay on top of things ourselves. And then we need to think kind of creatively about the relationship between the algorithms and the hardware itself, and try and understand what implications developments in AI have for hardware, and the reverse, what implications developments in hardware might have for AI. So we try and think about these problems, we try and innovate, publish, and generally push forward state of the art in hardware meets algorithms research.
What's your particular focus area that you enjoy?
I think broadly, there's this quite interesting idea of the hardware lottery that comes in a lot when we think about the relationship between these algorithms and the machines they run on. And that idea of the hardware lottery is basically the algorithms that sort of prosper, the models that do well and are state of the art right now, really are the ones that happens to work well on the current hardware we have. And it's kind of our job as a team to say, okay, well, if you had different hardware, would different algorithms have won out? Would we have a different set of things that would do well? Would it open up new capabilities in the whole AI space? So that's kind of what we're really focused on as a team. Can we somehow try and innovate in the space of algorithms to better suit alternative hardware? Because obviously that's what Graphcore as a company produces. It's different hardware to the mainstream. In terms of my personal stuff, I think a lot about the way in which we represent numbers in machine learning models. So think about how to most efficiently represent the distribution of numbers that get created when we train a model. And also think about the reverse problem. How can we design models that generate distributions of numbers that are easy to efficiently represent?
So on to Papers of the Month. Could you kind of give us a bit of context into why do you collate these papers together, and how do you collate and make this concise list each month?
So staying on top of machine learning research is a difficult task, and it gets harder and harder every year with more and more papers being published. This is obviously a problem we have as a team, because we need to understand what's going on and we need to stay on top of things. And it's a problem we have as a company as well. We all need to have some sense of what's going on. So one of the sort of responsibilities we take on as a research team is to say, okay, we're going to try and stay on top of all the papers. And for a while, we've been producing internally this sort of Papers of the Month service for everyone internally. So, you don't have to read all the papers. As a team, we all individually don't have to read the papers, but we can come together and kind of do a sort of team summary of the most interesting stuff that we see. And we've been doing this for a while, and we increasingly thought, this would be a really valuable thing to give back to the community and a way of engaging with the stuff that people have written. So can we put this out there as a public resource? And so that's really what we've been trying to do recently.
I'm so happy that you do collate this list, because it's really useful for me as well in my role to be able to get your expert curated list as well. So let's get into it. So we've got 4 papers this month that you want to present to tell us about. So let's start with paper number 1. Can you tell us what is the first paper that you've chosen, and why have you chosen it as your first key paper of the month?
Yes. So paper number 1 is a paper called Bad Students Make Great Teachers. Active learning accelerates large-scale visual understanding. So what is this? Bad students make great teachers. Well, the sort of the thing that really excited us about this paper was that it's one of these papers which takes something that you sort of take for granted after a while if you've been doing machine learning, which is just that the way in which we decide what data to look at is very naive. We basically sample uniformly from everything in our data set, which is basically to say, everything is as valuable as everything else and we're going to pick at random. Now, intuitively, as a newcomer to the field, you look at that and you say, that doesn't make any sense. And then after a while of working in the field, you just sort of take it for granted. And this unpicks that assumption. And, they're not the first people to try this, but they've really succeeded here where others have failed previously. So, really excited about this paper. And we think that, if it turns out, yes, this does work in a wide range of applications, then it could be something that everyone starts doing.
I really agree with you on that, about the intuition of using data uniformly, and that doesn't really make sense. Tell us what's the background, what's the context for this work?
Yes, so there is a whole sort of field of research on something called active learning, which you might even think of it as proactive learning. It's you trying to make a decision about what you're going to learn on, rather than just kind of taking the data that comes out of your sort of random sampling process. And people have done this a lot previously in supervised learning, which is some of the active learning stuff is more about selecting which data to attach a label to. But actually, when we're thinking about, say, large language models, we're in this sort of unsupervised space where the sort of labels you'd get in a traditional sense come from the data itself. We mask out some of the data and we're sort of filling in the gap, if you like. So in this sense, it's really just about, which chunks of data do we wish to train on? This masked sort of language approach or causal language modeling. What's the good data? What's the bad data, in a sense? So that's kind of the background. And there is this method you might call model-based filtering, which is all about trying to use an AI model to figure out what you should train your AI model on, which sounds like a bit of circular logic, and there can be problems there. But it does make sense, and we'll come on to why.
So what's the method that they introduced then? So, and I guess, how does it build on this initial model-based data selection that you just introduced? How does it build on that? And what are the key ideas?
Yeah, so I guess probably the key idea underlying this is the idea of being compute positive. So it's all very well having a method for telling you which data to train on, but if that method is so expensive that it defeats all the sort of total benefit of actually having that process, then it's kind of pointless. So you kind of need your data selection process plus the cost of training your model to be less than the original cost of training. And it's that compute positivity thing which no one has really been able to crack yet in a meaningful way using machine learning models. And that's what they've really made a breakthrough on.
I was just going to say, it's kind of ironic because you're building some methodology to improve your efficiency, but actually you end up spending a lot more compute in doing so. Yeah.
I mean, I think that's so common in AI research. Actually, people come up with a really neat new trick to make things more efficient, but it slows you down somewhere else, and overall, you've lost efficiency.
Yeah, 100%.
So the way in which this basically works is what you need is a method for scoring the data, and one of the sort of most interesting parts of this is this question of, well, what properties of the data do you actually care about? And it's a sort of very simple question here. Do you care about easy data, hard data, or some other sort of metric that takes these into account? And there's sort of two naive instincts here. One is to say, oh, well, we want to train on the hard data. We want to get smart. Give us the difficult problems. But it's a bit like going along to a sports match and starting in the top team or whatever. If you're too bad starting off, you're never going to make any progress. The other instinct is to say, oh, well, give us the doable stuff, give us the nice, easy stuff. That's what we can start with. We don't want to begin with too difficult a data. But that also doesn't work because you're only training on trivial things. At some point, you need to be challenged. So they have this idea of learnability, which is, if you like, you take a model which is already a decent model, which already has a sense of what's difficult and what's easy. And you have your own models while you're learning's own assessment of the data. And the key thing is, what's the difference between these two models' assessment of how easy the problem is? So if the sort of already fairly smart model says to you, this thing is easy for me, and you currently look at it and say, this is hard, that's a data point you want to train on. If both find it easy, then it's trivial. If both find it hard, then it might be impossible. So you want that gradient.
This is sort of curriculum learning too, right? Or could be.
Yes, there's definitely deep connections here with curriculum learning. Curriculum learning is focusing on a slightly different aspect of this problem. That's more about the order in which you learn. This is much more focused on what data is a high enough quality for you to learn on. So one of the things they do here is they've got this problem, right, of you need this reference model to tell you how good a sort of decent model, how hard a decent model thinks this problem is, this particular data point. And of course, you have a reference model, fine. You don't want that reference model to be too expensive. You want it to be nice and cheap. So you can use a small model for that, and that works okay. But you also need your own model to not be too expensive when you're doing this assessment. Because if your model looks at the data and says, oh yes, okay, we think this is medium difficulty, well, you've just incurred the cost of running your model over that data. Well, that already starts to be self-defeating. So the key innovation they have in this paper is to say they come up with what they call an online model, which is a sort of small model of your sort of big model that you want to train, your learner model. And they're training that at the same time as a sort of proxy for the big model. And so what this allows you to do is it allows you to look at the data and kind of estimate how difficult that data point is with this new model you're training up. You also have a sort of pre-trained small model that compares it against. And so this difficulty comparison, one person finds it easy, one person finds it hard, is only ever done between these small, cheap models. And that really is at the heart of this paper.
Yeah, so what were the experiments that they ran and the results that they got?
Yeah, so one of the experiments that they run to begin with is just looking at how smart you need this reference model to be. And it turns out that, yes, the reference model can be fairly small. They also look at whether you need to use your own big model to do an assessment of how difficult you're currently finding things, or whether you can delegate it to a small model. And it turns out that this delegation process works really well, and you can actually make the model really quite small. They go down to a model a thousandth of the size of the full model, and it turns out that, yeah, this tiny model is still good enough to give you an assessment of what's difficult for the model currently and what's easy.
I remember reading, skewing through the results part, and there's kind of different levels of efficiency improvements depending on whether you pre-train your model or...
Yeah, they have this quite nice figure which shows the kind of trade-off between how big this small model is and how much that saves you. So you do get hurt slightly by having this online model be quite small, but then it gives you substantial savings because that thing's so cheap to run. It means that actually, yes, you're not quite filtering the data as effectively, but you don't incur this overhead of running this model at all because it's so cheap you can basically ignore it. And you can make that model slightly bigger, and yes, it will do a better job of filtering out the data, but then it's going to add some overhead of itself. So there's a kind of trade-off there, and you want a model of just the right size. But basically, on a fairly large spectrum of these model sizes, it always gives you an improvement. So you don't have to get it spot on to get a win.
And these experiments will run on vision workloads or multimodal and vision, right? So is this extendable to other modalities?
That's a good point. This paper is just focusing on vision models. We're still thinking of vision transformers, so it's still that LLM paradigm, if you like, but perhaps not language. It's vision and vision plus language. A key question here definitely is, does this extend to language data sets? Because at the moment, you're thinking mostly about vision data sets. And a key part of this is about filtering for quality on the data set. So, okay, this might hold for a vision or a vision language data set. What about a pure language data set? Are those high enough quality that maybe filtering doesn't bring you that much benefit? So one of the things I guess we want to see out of follow-up work on this question is, can you do this for a language data set? Does it matter how noisy the data set is? If you have a really clean data set to begin with, maybe this doesn't help so much. Those are all valid concerns, and we still need, as a community, to understand the answers to those questions to really get the benefit of this. Having said that, it's not very expensive. So if you run it and it doesn't help you very much, you're not necessarily lost a lot, and you might gain quite a bit. So my recommendation to anyone sort of thinking about training up an LLM now would be try this. You've not got much to lose and you might have a lot to gain.
Great. Thanks, Charlie. Right, number 1 done. So let's move on to number 2. What is your second paper of the month? And why have you chosen it?
So paper of the month number 2 is Beyond Chinchilla-Optimal. And the subtitle is Accounting for Inference in Language Model Scaling Laws. And this is a paper from MosaicML. The idea behind this paper, and the reason we were sort of excited by it, is there's been this sort of whole series of papers over the last few years on scaling laws, so-called scaling laws for various models. And they keep getting updated. People keep discovering new things. And this is the latest version of that. Particularly, they're accounting for the cost of actually running the models rather than just training them, which is one of these practical things which is a really important consideration and hasn't been captured by the modelling thus far. And we're really pleased to see this in there because people started making decisions based on these kind of inference assumptions, and it's never really been reflected in the literature that we've seen.
I've definitely seen a shift just in the last few months, and I've mentioned this in a previous discussion with someone as well, a shift to thinking about inference and thinking about inference cost. And we've seen the models that are being published there's a lot of smaller models, longer training. So I've definitely seen this as a sort of trend. So I think this paper is really nice that it's captured that. So background of the paper and kind of introduction.
Yeah, I might give a sort of whistle-stop history of scaling laws work over the last few years because it's a really fun topic.
Right.
And that will really contextualize this because I think you need the context. So, okay, let's rewind to 2020. OpenAI released their paper, Scaling Laws for Neural Language Models. And this is a big, important paper. And basically what they do is they identify the kind of mathematical relationship between the loss of your large language model and each of the model size, the dataset size, and the amount of compute you use to train it. And they call this a power law. It's a power law mathematical relationship, and this is kind of what they use to justify the size of GPT-3, which is 175 billion parameters at the time. It's absolutely enormous. It's still pretty enormous, and this is a really important thing because what it means is, well, actually, we can start to estimate how good our model is going to be before we trained it up. And that's very valuable. And it also allows them, because they've got this mathematical relationship, to say, okay, if we want to go and spend another umpteen $1 million on training up a model, this is the optimal ratio of dataset size, model, tokens, all these things, in order to get the most bang for our buck. So this sits around for a couple of years and people start to train up very large models, and there's a bit of a competition as to who can train up the biggest model because there's a general sense that bigger is better, and they've said basically exactly this in the paper. 2022 comes along and DeepMind released a paper called Training Compute-Optimal Large Language Models, which is often referred to by the model that they trained up, which is a thing called Chinchilla. And they've got these Chinchilla scaling laws. And what they basically say is that actually OpenAI got it wrong in a sense. Their model was incorrect. There was a few quite technical things which I can go into if we really want about what they did wrong there. But basically they say, okay, you should actually scale the number of parameters linearly with the number of training tokens, which is a lot less than was previously said. So with these new Chinchilla laws, they'd previously trained up their sort of GPT-3 competitor, which is a thing called Gopher, a fairly chunky 280 billion parameters. And with this new paper, they've got this thing called Chinchilla. It's now 70 billion parameters, but exactly the same compute cost. So they trained it on, it's a quarter of the size, trained on 4 times the tokens, and it's quite a bit better than their Gopher model. So this has blown out the water the idea that this enormous sort of model trend is the right thing to do. Bigger is still better, but it's just the ratios were kind of off. Okay, so that happens. Now a year after that, we have Llama come out, which is the open source large language model from Meta. I'm sure lots of listeners will be familiar with this. And they've got their biggest model. It's about the same size as Chinchilla and trained on about the same number of tokens, 65 billion parameters. But they also train a 6 billion model, so a tenth of the size, and they've trained this thing on 1 trillion tokens, which is far, far more than anyone ever thought was sensible. It's the same number of tokens they trained their 65 billion parameter model on. And you might be scratching your head looking at this thinking, okay, well, was the scaling law that Chinchilla had wrong? Did DeepMind also make a mistake? That's not the case. It's just that Llama were very specifically accounting for, when they trained up this model, the cost of doing inference on it. So they were looking at this thing thinking, and they've got a good quote in the paper actually, so I'll read this one out. So this is from the Llama paper. Although it may be cheaper to train a large model to reach a certain level of performance, a smaller one trained longer will ultimately be cheaper at inference. So that's from the Llama paper, and this is basically the direct justification for the paper that we're now covering in this Papers of the Month, which is accounting for that inference cost. So there's the history.
Cool. So maybe take us through the Mosaic paper, what they've done.
Yes. So I won't go into exactly the equations because it's a little hard to describe verbally, but it's actually fairly straightforward what they do. So the Chinchilla paper gives you these equations, and it just describes this mathematical relationship between the loss and the parameters, number of tokens, amount of compute used during training. And they just add a term to account for the inference. And then you've sort of got to rejig the maths a bit to solve this optimization problem of exactly what the right ratio is. But that's, details for the appendix. Essentially, they've added this extra term to account for inference. They do two steps of this. The first one is just a very simple one to say, okay, we're going to add an extra term for the number of tokens in inference. And the second one, they go into a bit more detail. The first one is what they call a compute optimal model, and the second one is a cost optimal model. And that second one, they add in all these extra terms for the utilization of your hardware at different stages and accounting for the difference between your sort of pre-fill stage when you're doing generation and your actual token generation. But all this to say that what they're really doing is accounting for the practical aspects of doing inference.
The second equation felt more like the closer to real world.
Yeah, 100%. They actually outline a few, so I can go through a few of the things that they're trying to account for.
Yeah, what are the things? Yeah, it's quite interesting. What are the things that they try to account for?
So, the first thing that they look at is this utilization problem. So, particularly inference, it's something that those of us who think about hardware are very familiar with. That token by token generation is not nearly as friendly to hardware as training is. In training, you can really easily parallelize things across the sequence that you're training on. But for actually generating the tokens, you've got to do it one token at a time. And so what ends up happening is you've got these big compute units on the hardware itself that are sat there doing nothing for most of the time. And you're just waiting to load up weights or sort of cached activations from your model just over the sort of bandwidth you have from your chip to your memory. And you're not actually doing useful work here. So that's something they account for. They're also accounting for the ratio of the sort of at generation time, the input sequence, this sort of pre-fill stage, and the actual number of tokens you generate, that ratio is quite important. Whether you've done quantization of your weights for inference, whether you're using hardware which has different properties and so on. So there's a few things they're accounting for there, and perhaps some things that I haven't mentioned, but that can come under the sort of heading of utilization more broadly. So
what are the results? There's kind of a sort of summary conclusion of, in general, what does the paper show?
The paper basically shows that if you want a sort of one-line takeaway, it's train a smaller model for more tokens if you're assuming it's going to get used a lot, which I guess is pretty much everyone's assumption, because why would you bother? Unless you're in a research team and you're just doing it for research purposes. But if you're going to spend a bunch of money on a model, you're hoping it gets used. So I think what it basically does is it just moves the dial again in that direction of smaller models that see more tokens. And there's even things that they don't account for there, which would make you want to train an even smaller model. So they don't account for things like the latency advantages of using a smaller model, that actually it's going to spit out tokens faster. And that's a really significant benefit. They're not really looking at the sort of practical benefits of just, this thing takes up less memory. If I need to send it over to, store it somewhere or send it somewhere, it's easier to manage. It's going to fit on a smaller machine, all these things. So I just think that it's obvious now that when they were doing the GPT-3 training stuff, they got very carried away with big models, and perhaps for good reasons, but this massive correction has taken place and we're now into a smaller model world.
That's kind of the reason I enjoyed that you chose this paper. It sort of brought two themes for me that are very much at the kind of forefront at the moment, which are train smaller models for longer, but more performant smaller models and think about inference. And I feel like those two ideas are kind of more and more important. Yeah. Cool. On to number 3, Charlie.
So paper number 3 is analysing and improving the training dynamics of diffusion models. And this is a paper from NVIDIA.
This was also published in December, I think, but got lost in our December-January holiday NeurIPS season.
Yes, we're taking a slightly generous interpretation of the word month in papers of the month, but I'm blaming Christmas for that. So there's a few sort of December inclusions here, but they're good papers, so I don't mind.
Yep, and the authors of this paper are also the authors of StyleGAN, I believe.
Right. Yes, I think I recall that.
So why did you choose this paper?
So one of the reasons we're interested in this paper is because it has a lot of overlap, in fact, with some of the stuff that we've done internally, thinking about training dynamics of models and stability in some of the training signals that go through the models. Now, I've looked at this in some of my work in relation to numerics, so how we can represent the numbers that are generated, and it turns out having nice stable signals throughout training is really good if you want to squeeze those numbers into as few bits as possible when representing them. But it turns out in this paper, and there's been other similar work along these lines that we've been interested in as well, that actually this can just be really beneficial for the quality of the final models that get trained up. There's all kinds of complex interactions that we don't necessarily understand within the models that can get exacerbated by this thing blowing up over here, this thing shrinking over there. And if you can get a handle on those things, control them, practically speaking, that process of back propagating your gradients, updating them by fixed learning rate and so on, having a learning rate schedule to control how those updates sort of scale as you go on through training. All of that stuff kind of is based on certain assumptions about, well, these things should be fairly stable, and actually in a lot of machine learning models they're not. And so they've really sort of dug into this here in the specific case of diffusion models, and they've gotten some really, really good looking results.
Yep, agreed. So could you take us through a bit more detail of the paper, the background, and the key ideas?
Yeah. So as I said, this problem, particularly in diffusion models they have, is noise in the training signal, and things such as your weights or your activations are starting to grow in different parts of the network. And what they say is, and take a quote from the paper here, to learn efficiently in such a noisy training environment, the network should ideally have a predictable and even response to parameter updates. Very simple idea, but it turns out almost all current machine learning models fail to meet this sort of criterion. And they sort of suggest that, okay, this might actually be holding us back, particularly in the case of diffusion models, which can be quite fiddly. And the solution to that is really just to start tweaking bits of the network and to throw in sort of clever ideas here and there to try and stabilize them.
Yeah, so they analyze sort of different dynamics and come up with a whole load of suggestions to tweaks. So yeah, what are the changes that they make to the diffusion models? Yeah,
so the way in which they present this, the changes that they make is really helpful here, and it's very good sort of researcher practice, which is to say they come up with these different sort of configurations, which are just sort of groups of changes they make, and they apply them one by one, and they train the model with each different configuration, and they look at how much the loss goes down, or the metric that they use to evaluate these models changes with each innovation. And so you can see how much each one adds. You can kind of see that every change they make brings a benefit, which is something you don't often get, or there are definitely some culprit papers which don't give you this, and you're sat there looking at the things they add thinking, well, which bit of this helps and which bit of this is kind of incidental. In terms of what they're looking at here, so we're talking about something they call the ADM architecture, which is think DALI, Stable Diffusion, Imagen. This is the kind of backbone they use here. So yeah, there's lots of little things. So they are going to do a sort of normalization of the loss that flows backwards through the network. They're going to switch out the attention mechanism for a slightly less spiky attention mechanism, and that's sort of helping things. They're going to, they do a lot of work normalizing the weights in the model. So they have a couple of schemes of this. And basically what they end up doing is every step of the network, every time you do a parameter update, you you divide the weights by their own magnitude to get them back down to this sort of unit scale. And then even the forwards pass, despite the fact they've already done this, they renormalize the weights to help with, it's quite a sort of technical thing about the direction of the gradients, but they're really aggressively sort of managing the scale in these networks and the magnitude of the vectors that are sort of flowing through. They look at activation functions and see how they can sort of normalize these things. And, this can all get quite technical, but the key takeaway message here really is that to look at every bit of the network, to understand the effect that that bit of the network has at every forward pass and say, how can we add in the opposite sort of compensating factor to get us back down to this sort of stable point?
I can see why you like this paper, Charlie. It sounds very similar to the kind of the way that the unit scaling paper from you and Graphcore, other team, was that was published last year, was kind of developed.
Our scheme was to say initialization, so just before you train, let's get everything perfect for this first forward pass and backwards pass. What they're doing is they're saying, no, we're going to maintain this property all the way throughout training. So every time we touch the model, we're going to sort of readjust things. So they're quite aggressive in doing it. The worry is two things. One, you're sort of overly aggressive and you restrict the amount the model can express itself, but they've managed to compensate for that quite smartly. And the second point is this going to add a lot of practical overhead? Is it going to be just slower to run this model? Now, I didn't delve through every minutiae of the appendix, but I didn't see any real analysis of that. So I'd be interested to know quite how much it adds. But, it helps. It seems to help so much. And we talk about the results that maybe it's worth the overheads anyway.
So the results were pretty amazing, weren't they?
The results look very impressive. I mean, sort of full disclosure, I'm not a sort of diffusion person. So I often find that in fields where you're not really plugged in, the hardest bit to interpret is the results, because they spit out a number and the numbers always look fantastic. So it's sort of delving in. But I mean, they have this sort of plot in their figure 1, which shows their results versus a load of other sort of very high profile methods, and they not only do they beat them, but they beat them using a lot less compute. So it looks fantastic. I guess the proof in all these things is always, does this get picked up and used by other people? But I can definitely see this getting used a lot.
There seems like there's kind of an additional kind of part to this paper, which is the EMA result that they find, which actually seems to be almost as important or maybe even more important than the rest of the results.
Yeah, 100%. I first came across this paper when I saw someone on Twitter praising this paper for basically having a little paper within the bigger paper. And that little paper is this technique they call post hoc EMA, which is a really neat, simple idea, but one that's going to have a lot of big practical benefits. So just a sort of quick intro to what this EMA thing is. For diffusion models, it turns out it's really important for your final model to actually not just be the thing you got at the end of training, but while you're training your main model, you're also kind of storing this exponentially weighted moving average of all the weights you had throughout training alongside your sort of main current weights. And you're going to take that exponential average of your models as your kind of final model. And that will be better than just the thing you trained up raw. The problem there is that this moving average of your model weights, well, it needs some sort of weighting. You want to weight the later things more than you want to weight the early things. And how do you do that weighting? You can come up with some sort of factor. You can sort of, in this exponentially weighted moving average, you can put in a sort of weighting factor. But you can only put in one of those factors, and then you train up, and then you get the final model out. What if a different factor had been optimal? You have to train all over again. And that's, I guess, what people have been doing here. But it's hugely expensive, especially if this hyperparameter, this sort of exponential weighting, is really important for the final model performance. Well, are we going to have to train up 10 of these every time we want one? That seems like a huge overhead. And so what they've basically done here is said, we've got this really neat little trick, and it basically allows you to kind of approximate any one sort of weighting that you might want to use using this old method with their new method. And basically all they do is they say, okay, throughout training, we're going to take a bunch of kind of checkpoints of our weights and save those. And those checkpoints will be exponentially weighted averages of the weights we've seen, but with different weightings and, at different points. And once you've got all these at the end, it turns out that you can just kind of do a linear weighting of all these different checkpoints to kind of artificially recreate different sort of averages. There's a nice sort of curve in the paper which makes this quite clear. It's slightly tricky to explain, but the bottom line is that this really expensive process that you'd have to do multiple full training runs to figure out the right parameters for, you now just can do it once and sort of mishmash this thing together at the end, which will create as pretty much the right sort of shaped average.
So on to our final paper of the month. What's number 4, Charlie?
Number 4 is solving Olympiad geometry without human demonstrations. For this paper, we wanted to get a balance in papers of the month, and it's quite nice to have a more applications-focused paper. And this paper was, it's sort of so incredible in some aspects that we sort of felt we had to and really wanted to include it. So yeah, it's a DeepMind special. It has the word alpha in it, so you know it's going to be good.
And it was published in Nature.
It's published in Nature as well. Another good omen.
Great. So can you give us some background on the paper?
Yeah. So there's been obviously a lot of work over the last couple of years of showing how large language models can be quite good for sort of mathematics, coding, reasoning style problems. And there's been some really good results on some mathematical benchmarks. Geometry specifically has been a tough nut to crack because of a lack of training data specifically. Now, geometry questions, think, triangles and circles and lines on a page. We've got to figure out, relationships of angles and things. That is inherently going to be difficult to generate training data for because A, the problems are all very visual, and B, whereas in some other domains, there's actually quite a lot of human proofs translated to machine-friendly languages. In geometry, that there's a bit, but there's not a lot because it's quite naturally difficult to express some of this stuff.
So what were the, if you can recall, what are the types of models that were used, were the state of the art before alpha geometry for solving these kind of problems? Yeah,
so stuff that was state of the art before this was, really kind of pre-deep learning, symbolic, search-based systems. I think people have tried a little bit of LLM stuff on it, but without much success. And they have results later in the paper which show what happens if you just use sort of plain GPT-4 on this out the box, and it gets 0 out of 30 on their test set. So that is all to say, you can't just throw a standard LLM at this and hope it's going to solve it.
So previous state of art was symbolic engine. GPT-4 doesn't work on its own. What's the alpha geometry solution that they came up with?
Yeah, so you've got this problem, right, of a lack of data. So the first problem you're going to have is generating that data, and the second problem is using it. So they create the problems and the solutions to those problems synthetically. They've got 100 million problems that they've created synthetically, and they're going to train on these. And the thing I really like about this paper is that they've got this really nice balance in the problems that they generate and the way they solve them between what stuff you get the LLM to do and what stuff you delegate to a more traditional search-based system. So when they generate these problems, they kind of break it down to 2 steps. There's the sort of hard part that's difficult for these search-based traditional systems to solve, which is something quite technical called auxiliary construction. And then there's the sort of easy bit, which sort of follows on from that. So if you like, it's a bit like, I'd use the analogy of doing a Sudoku. You would stare at one bit for ages, suddenly fill in a number, and then a bunch of other numbers just automatically kind of almost fill themselves in because it's obvious. And then you've got a problem again, and you stare at it for a while. Sometimes you might have to make a sort of intuitive guess, and then, a bunch of other things unlock themselves. So they've managed to get this nice split between making the LLM do the bit which it's good at, which is the kind of intuitive sort of solving a problem where there's loads of different options and you just kind of have to have a good hunch bit. Maybe it's a bit more precise than that, than just a good hunch. But and then the bit the LLM is probably not very good at, which is just crunching through these necessary implications. One of the reasons why GPT-4 can't do this is just because there's a lot of like hard logic you have to do. And so they've got a really nice split here. And it's one of the reasons it works so well.
Yep. So there's kind of 2 big, again, this is why I really like this paper as well, because there's 2 kind of big themes here, which I think are both, again, big themes of kind of the year and the moment, which is the synthetic data generating 100 million, I think it was. So generating all of these examples synthetically. And the other thing is, multi-model, using kind of different models together, working together to solve a problem, which is definitely the way I think we're going. So do you want to tell us a bit more about how it works? There's kind of a looping, you sort of touched on it, but...
I got the impression there was a really nice tie-up of expertise between people who worked on this problem that obviously really knew machine learning and LLMs and so on, and sort of domain expertise, understanding the intricacies of what it means to solve one of these geometry problems, which lets you understand where to plug the LLM in, where to plug the traditional system in. And so I always think that's a really fruitful thing that we sort of see a lot of breakthroughs being made in areas where you really understand the problem domain well enough to know where the LLM goes and to know where the more traditional software system goes and to get these things talking to each other. It's really nice. It's easy to think that LLMs are going to solve all our problems, but in fact there's some stuff that we know as humans that traditional software is much better at than humans are, and in some sense it's going to be better than the LLMs as well. So if you want to solve a certain class of problems, understanding how these two things go together using your domain knowledge is going to be really key, and I think they do it really well here.
Could you tell us about the kind of results that they got? What is the International Mathematical Olympiad Challenge, and how have they put these questions together for the test set?
Yeah, so the Olympiad is it's a pre-university mathematical challenge. It's an international thing. I think there's sort of national stages and then there's sort of big international one, and it's all very intelligent, precocious young mathematicians go and attack this thing. They have this criterion, which is that they want all the problems to be understandable by someone who's not done university maths. The solutions are going to require much more complex maths, but anyone with a reasonable sort of grounding in maths is going to have a sense of what the problems are. They just won't understand the solutions. So that's the Olympiad. In terms of what this actually tackles, and it is, I would say it's a reason not to get too carried away with this paper. I'm still quite carried away, but not to get too carried away, is that they only limit this to, not only are they only talking about the geometry problems here, they're limiting it to a subset of just the Euclidean plane geometry questions, which is not all the geometry questions they have there. Of these, only 75% can they actually represent in the format they need to send it into their solver. So they're not really solving all the problems. It's a fairly narrow set, and it means that actually from all these Olympiads they looked at, they only get a test set of 30 problems. But yeah, they get down to this set of 30 questions. And as I said, GPT-4 gets 0 out of 30, so bad baseline. The sort of more traditional methods are getting like 10 out of 30. When they apply so they've got these two stages, right? They've got their LLM and they've got the non-LLM bit of their solution. The non-LLM bit on its own gets 18 out of 30. So they've done some pretty smart things with that. When you plug the LLM in, you start getting to like 25 out of 30, which puts you up to gold award level IMO, this is the best of the best standard. So there's still a few students that are beating you here, but you're beating most of the competition, and the competition is already extremely refined. So it's a really great result.
From what you just described, I can already feel some future work coming soon. So this, the Alpha of Geometry obviously only tackles a very a subset even of the geometry questions. Is this something that could be applied and generalized across other mathematical subjects or sciences? Or
yes, no doubt, but with the sort of caveat that they only really solved this problem, at least here, because they understood the intricacies of the problem, were able to synthetically generate the data set with an awareness of the fact that you have these sort of auxiliary what do they call them, auxiliary construction elements of it, where you can plug the LLM in. And so it's not like you can just plug and play this approach into anywhere else. You've kind of got to understand those domains. And it opens up, I guess, a sort of interesting question of, well, if you want your sort of really smart AI, we're working towards AGI or whatever, to be able to, just out the box do geometry, is that a realistic approach? Are we always going to need, like a human, fundamentally to get a good geometry AI is going to have to sit down and do lots of hard geometry problems with, it's not quite a specialized curriculum, but it's a bit like that. You've sort of got the right classroom set up for these LLMs, put them in the right sort of wider systems, and then they get good at them. Well, it doesn't say to me reading this paper that you can just take this method and apply it to all kinds of other problems and you're going to get great solutions. But the broader approach by which they've solved this problem is very applicable to all kinds of scenarios where you don't have enough data. You have to plug into external systems. And I can sort of see a world in which, if you want your LM to be good at geometry, you're going to go away and feed it into, one of these geometry systems. You're going to get some smart people to construct synthetic data sets, and you're going to have a sort of adapter that plugs into your, llama model, which suddenly makes it good at geometry. And that's going to be an important area of work to understand, how are we going to get our LLMs to interface with, some important API. Maybe it's talking to a, Salesforce API for your business needs. Well, great, we're going to go away and we're going to generate some synthetic Salesforce API calls and train it up on that, and it's going to plug in and suddenly, it's going to have this really useful real-world application. So, yeah, I'm really inspired by the sort of broad approach they're using.
Great. Thank you, Charlie. So that was the 4 papers of the month. And maybe finally, could you tell us, how do we find your blog so that we can go and read more about your papers of the month?
Yes. So the blog is a very new thing. It's coming out. We're releasing it for this edition of Papers of the Month. We're going to put lots of content on there about all the stuff the research team is doing. These monthly paper summaries, anything we do in terms of releasing new blogs or papers will be on there. If you want to find it, go to graphcore-research.github.io and it will all be on there. We also have a Graphcore Research Twitter account, a new thing, and a Threads account as well. So there's lots of energy in 2024 for the research team to put out new things, and we really want to sort of engage interested people in it and just have conversations with people. So if any of this stuff seems interesting to people, we're always looking just to kind of chat to the community and hear what they have to say.
Brilliant. Thank you, Charlie.
Thank you.
If you enjoyed this episode, then please subscribe to the podcast, leave us a review, or reach out on social media @DistillationPod. The Graphcore research team will be releasing their Papers of the Month write-up every month. You can find it on the Graphcore blog. And we'll try to catch up with them regularly here on the podcast to get their take. This show is produced by Ian McKenzie. Thanks for joining us. See you again next time.